All right, good. And so I can take this off?
Yeah, you have the choice to take it off as well.
Okay.
Okay, so we should start on time today because of a class that's going to begin here from 2:30. So we'll have to get out of here by 2:25, just so everybody knows. Okay. So today we're very lucky to have Anatoly Dymarsky here from the University of Kentucky. So, so I think you started at Princeton as a student and then went on to a postdoc at Cambridge in the UK, followed by faculty positions in Skolkovo in Russia and now in Kentucky. And Anatoly is going to tell us something exciting about symmetry breaker.
All right. Thank you very much for an opportunity to be here and speak. I'm very happy. This is my first trip after all this pandemic situation. This is my first in-person trip to give a research seminar. I will be speaking about an ongoing project based on one paper which was published already, or was posted to arXiv already, and another which hopefully will be posted fairly soon. And it is done in collaboration with Misha Goikman, who is a postdoc here. I don't see him in the room, but he's somewhere around, I'm sure. Now I see Misha. Okay. So what is the topic? The topic is persistent symmetry breaking. And first, I want to explain what it is. So let's start with something conventional, spontaneous symmetry breaking. Of course, it's a very common phenomenon, both theoretically and also in nature. In particle physics, we all know that spontaneous symmetry is responsible for the Higgs mechanism and standard model. That's how all particles get mass. And we also know, at least in the context of early universe, that if you hit our universe to a certain critical temperature, the symmetry will be restored. And that's why back in time, if you go back in time toward the reheating area, then symmetry would be restored. Now, this behavior standard model, I'm referring to standard model because perhaps this is the most common example for people coming from the high energy part. But this behavior is, of course, completely common and exhibited by myriads of other theoretical or even real condensed matter systems. You have a global symmetry, and at zero temperature, the system, the symmetry is broken. The ground state doesn't respect that symmetry. And then this breaking pattern usually continues for a certain range of temperatures, but then at a certain point, there is a Curie temperature when the symmetry is restored. You have a phase transition. So that's how we think about the situation in general. And then the question we have is the following. Is this conventional behavior, is it set in stone? Are there any exceptions? Are there special situations when the behavior of a system is different? For example, it could be that at zero temperature in the ground state, the symmetry is restored, but as you hit the system up, the symmetry is broken. And that is uncommon, but that can happen. And I will talk about this a little bit. But then you want to know if the symmetry is broken at some temperature. It doesn't matter what happens at zero temperature, but if the symmetry is broken at certain intermediate temperature, how far you can push the point of Curie point when the symmetry is restored again. Is it possible that when you hit the system up to higher and higher temperatures, the symmetry continues to be broken? That's the question. It sounds a bit fantastic in a sense that we don't see systems like that in real life, and we don't know many theoretical examples, but that's the question I want to ask. So more formally, I will be thinking, I'm trying to get attention and interest from the condensed matter community as well. So while thinking about that, I'm thinking about lattice systems, but in my talk, I will be focusing on field theoretic systems. And I want to ask the question more formally in the following way. Is it possible to have field theoretic system which will exhibit spontaneous breaking of a global symmetry? Could be discrete or could be continuous. And I want this pattern of symmetry breaking to continue to arbitrarily high temperatures or arbitrarily high energies. Now, since I said field theory, I should specify that it should be renormalizable or UV complete model, because if I'm talking about effective model, then there is no much merit to speak about field theory. I can be speaking about lattice as well, right? some low energy description. So in my talk, I want to focus on UV complete models, and I want them to be unitary in d+1 dimensions. So let us introduce the notations. Small d will stand for the number of space and time dimensions, and capital D will be the number of space dimensions. So as a theory in the physical space-time with the time, I want it to be unitary. Of course, as an effective Euclidean theory which describes statistical mechanical system, it doesn't have to be unitary. That's okay. Statistical mechanics, quantum field theory doesn't have to be unitary, but here I want it to be unitary. So that's what I want. I want to be complete and unitary theory, otherwise well-defined theory, relativistic, because that's what I know how to do best, and that's what we think is happening at fundamental level. But I want the symmetry to be broken at arbitrarily high temperatures. Yes?
Particularly with respect to condensed matter application. Do you think that this will happen for a set of models which have some space in parameters, or for particular models such that you change model a little bit and immediately find the temperature?
Based on what I will be talking about today, this should not be, this should be a robust phenomenon in the sense that you can move in the space of theories and a space of models. So it's not like integrable point where you move away and it's completely broken. But this is only informed by the model I will be talking about today. And this model has its peculiarities. So, yes.
Are you interested only in zero-form symmetries here, or one-form symmetries as well?
I'm only interested in conventional global symmetries, just because that's what I have been thinking about so far.
Because there's a very easy example with one-form symmetry.
Yeah, well, it's a gauge symmetry, right?
No.
Oh, you mean
symmetry?
Global symmetry? No, I'm talking about just conventional symmetries. Just conventional symmetries. Okay, so we don't really know any system like that. At least that's the conventional lore. We don't know any system like that. That's something completely exotic. And there is a good reason why we don't know any system like that, because actually there is a number of theoretical results which tell you that what I want is essentially impossible. And the simplest argument comes in the name of Coleman theorem. And in field theory, that's a very, very simple theorem. I'm, of course, oversimplifying things even more, but it basically says that if you have effective two-dimensional theory, then it cannot have a Goldstone boson, because Goldstone boson is a massless particle, and you will have an infrared divergence. You try to calculate the tadpole diagram, it's logarithmically divergent, and in certain circumstances, you subtract the divergence, and that's physically meaningful. But in many situations, that's not okay, because if it was a UV divergence and you are thinking about condensed matter system, you say, I modify physics at the lattice scale, and that's how I subtract my UV divergence. But with the infrared divergence, there is no normal way to do it, because you can make your system infinitely large, and you still want the answers to be physically meaningful, to be finite. But that's in field theory. But then there is also a theorem called Mermin-Wagner-Hohenberg, and sometimes people also mention Berezhinsky in this context. It's a theorem which says that if you have condensed matter system in two dimensions, now you don't have time, then you cannot have spontaneous breaking of a continuous symmetry at finite temperature. It's a no-go theorem, and the basic argument goes like that. I'm oversimplifying, but the basic argument goes like that. Imagine that you have effective Euclidean field theory which describes this phase transition at finite temperature. Then you will have an associated Goldstone boson, which is an order parameter of your broken symmetry. And then you want to calculate, so you have an ordered phase. In a spontaneously broken situation, you have an ordered phase. So you have an order parameter which has expectation value, but at the quantum mechanical level, you want to know what's the variance of that order parameter. You measure it, and there will be some uncertainty. You want to know what's the variance. So you calculate the variance, and here Coleman theorem tells you that the variance diverges, but it basically means the variance is infinity, and it makes no sense to speak about the value of the order parameter, because if you start measuring it, the values will be all over the spectrum. There is no definite value of the order parameter. So basically that means that you cannot speak about an ordered phase where sigma, which is a Goldstone boson, Goldstone mode, has any value. Not sigma squared, just sigma itself. And you should speak about disordered phase where value of sigma will be either 0 or will be all across the spectrum. Okay, so this is a theorem. It's rigorous, but it doesn't include discrete symmetries because discrete symmetries don't lead to Goldstone boson. And also it doesn't work in higher dimensions. If I have a three-dimensional system in real space, then there is no analog of this theorem. So, okay, there is a good no-go result, but it's not completely universal. But that's not all, because I can think about lattice systems. And depending on your taste, let's go with the simplest lattice system, which has maybe fermions on a lattice or Potts model on a lattice or something like that. Importantly, I will require that local Hilbert space, the Hilbert space on each lattice side or an edge, doesn't matter, is finite dimensional. And in this case, you can actually define infinite temperature because the number of degrees of freedom or the dimension of the Hilbert space is finite. You can heat your system to infinite temperature. That's a well-defined notion. And in that case, the density matrix will be just proportional to the identity, and there could be no other parameter. Okay, so it's a completely trivial thing. Of course, if you try to make it more mathematical, you need to be very careful because you want to define maybe free energy as the simplest thing. You maybe want to show that another parameter will have 0 expectation value, or maybe you want to show that free energy will be an analytic function. And basically, you define this function as a function of beta, and you want to show that it's analytic in the small vicinity of beta. And for a range of lattice models, you can do it very rigorously. You can show that it's a function with at least finite range of analyticity. And then when this analyticity ends, that's where Curie point is. And you can have very robust bounds that Curie point cannot come closer to 0 than certain value. Okay, so it's completely clear that if you have a lattice, you cannot have persistent symmetry breaking. You hit the system to infinity, that's all. Okay, that's perhaps the argument why we never see persistent symmetry breaking in nature, because everyone around us is made out of atomic lattices, and that's why we cannot realize that. But of course, there are also loopholes here, because, for example, if the dimension of the local Hilbert space is infinite dimensional, you have bosons on the lattice, then to provide an analog of this theorem will be very difficult. And I do not know if an analog of this theorem exists. It's an open question, at least for me. And there are also other possible ways to avoid this theorem, which I'm going to talk about later in my talk. I don't want to announce them just now. Okay, I started with more rigorous arguments, but then as a physicist, I always want to have a very simple and very universal argument, which will sort of explain what's going on. And we have an argument like that, which will prohibit symmetry breaking at very high temperatures. Intuitively, if you have some microscopic description associated with symmetry, like a vector rotated, directed somewhere, you understand very clearly that if you have an ordered phase, it means that your vectors are aligned in one position. If you have disordered phase, it means that they're all over the place, which means that disordered phase should have larger entropy, larger number of microstates. And since this is finite temperature physics, we are looking for free energy, which is energy minus temperature entropy. If entropy of the disordered phase wins, then at sufficiently high temperatures, I expect the disordered phase to always win. Of course, this is again not a rigorous argument because I appeal to certain microscopic description and maybe in terms of field theory, weakly coupled description, because I need to speak about some vectors, and those things might be only defined well in the weak coupling regime when I have a Lagrangian of my theory and everything. But in that settings, it seems like I can never have symmetry breaking at sufficiently high temperatures. So this is something to keep in mind if I actually want to produce a counterexample. Finally, I have the last argument, which is less intuitive, and it's not clear how rigorous it is, because basically I am connecting the question of symmetry breaking of high temperatures, the question which we don't fully understand, as I will try to explain today. We don't fully understand it in field theory. I want to relate it to another question, which we don't fully understand in the context of quantum gravity. If you have a field theory, which can have a holographic dual in terms of classical gravity or quasi-classical gravity, then thermal phase at large temperatures will be described by a black hole. If it's a small temperature, then it's not necessarily a black hole, but above certain temperature, it will be a black hole. It will be Hawking-Page transition, it will be a black hole. And if it's a black hole, we know that it has no Hare theorem, which says that it cannot be charged under any global symmetry. Otherwise, you will have certain additional quantum numbers in addition to those standard ones. So it looks like if you can have an example of persistent symmetry breaking, you will be going against certain conventional law in quantum gravity, which is interesting. And it's interesting and thought-provoking if you can actually make an argument, if you can make an example which will have unusual black hole as a holographic dual. So this interesting connection between persistent breaking and black hole I heard for the first time from Zahar Komorgotsky, who ignited my interest in this topic and interest of other people. And that's perhaps one of the motivations to think about this, because there is some interesting connection to gravitational physics. Okay, after so many no-go theorems, it's completely obvious what I want to do next. After I explain why things are not possible, I want to give you an example showing that it is actually possible. That would be the right way to structure the talk. So the first example comes from Weinberg. You start with the heavy guns. Weinberg himself had an example which achieved something very non-trivial. Weinberg was considering vector models. It was back in the 70s. He was considering vector models, and he was considering how those vector models behave at finite temperature. And he saw very clearly that if you have one vector model, ON, something like that, it could be ON with different fermions and different couplings. He was considering different scenarios. Symmetry could be broken at low temperatures or maybe zero temperature, but then above certain temperatures, the symmetry is always restored. And then he considered two vector model. He considered with this equal ranks of the global group. And it was in 3+1 dimensions. There is no Mermin-Wagner theorem in 3+1 dimensions. There is no-go theorem against continuous symmetries. And he found something very, very interesting. He found that there is no symmetry breaking at low temperatures, but above certain temperature, there is a symmetry breaking. And then, of course, it persists to infinite temperatures. That's a counterexample right away. But
how these theories were connected to each other?
Through
just two quarters, it doesn't help, right?
That's exactly right. Through a quartic coupling of some sort. I don't remember exactly if it was fine-tuned, but it was a quartic coupling, of course.
But it gives a maximum temperature, maximum energy above which it's probably not applicable.
Well, the problem with this model, just let me answer the questions and then I'll come to yours. You have a question, right?
Go ahead.
So why this is not the end of the story? You have a counterexample why we don't stop here. We don't stop here because that model is not UV complete. So this is a scalar model which has one dipole. It's not well defined above certain temperatures. Just one second. Above certain temperatures. So thinking about this model, I would say, well, nothing catastrophic happens. Nothing radical or revolutionary happened. I probably have a field theory which is describing some infrared dynamics of a lattice system. I have spontaneous symmetry breaking. As I hit my field theory and enter the UV phase, I probably see the lattice and the symmetry is restored at that point. So there is nothing completely crazy happening in this case. Yes.
Before the system goes into a very high temperature region and understand that it's not really complete, what about entropy?
Right. So I don't fully, it's a great question, which I wanted to finish my talk with, because I also have an example and I don't understand the entropy argument for that example. So that's a question I wanted to finish with. I don't fully understand what happens there. That's something I'm thinking about. And also it's important to understand what happens with the entropy argument, because I'm forced to jump to my conclusions, but that's okay. I will repeat conclusion twice. That usually works well. I also want to understand if I can have a lattice example. And to have a lattice example, I need to understand well what happens with this entropy argument. So that's something I'm thinking about right now.
Can one calculate? I think one can calculate entropy for ON cross ON.
Well, he calculated free energy and he saw that,
Sure.
Yeah.
Yeah, and then what? Entropy in the ordered state is still smaller than entropy of the disorder.
Yes, probably. It has to do with the energy as well. It has to do, there's E minus TS. There is also energy,
But then it does depend on temperature.
but it could depend on the value of the field. You have a potential for the field, and if the field acquires some expectation value, you can change the energy. Okay, so this is one example, and Weinberg himself points out that there are real materials. He in particular in the paper speaks of Rochelle salt, which is a ferroelectric. So that's a material which exhibits no breaking at low temperatures, but if you hit it above certain temperature, it breaks symmetry. But for my talk, I didn't want to use that analogy because for Weinberg, it was more interesting that there is no symmetry breaking at low temperatures and the symmetry breaking at high temperatures. For me, it's more important to see what happens when you heat systems up. And my knowledge about real systems is limited, but my understanding is that if you have a ferroelectric, then if you hit it even to higher temperatures, there is always Curie point and the symmetry is restored. At least that's what the texts I found tell me. So maybe there is a better analogy here would be with the ferroelectric behavior, because if I understood correctly, ferroelectric materials can show this pattern of symmetry breaking even to very high temperatures. Of course, for the sake of the argument, you can say you can always hit your system until it starts melting. That's essentially UV scale for the crystalline lattice. And of course, nothing will persist beyond that scale. But if I understand correctly, up to that scale, ferroelectrics can show this behavior. At least this is a possibility. So anyway, we clearly see that the problem with this model, at least theoretically, is that it's not UV complete. Yes.
Just to clarify, what's your definition of UV complete?
Well, in the
two possibilities. One is the minimal model. It's a lot of code somewhere, right? The other possibility is this model is not UV completable. I cannot add other scalar field into the model to change the RD of the model just to make it flow slower or whatever. Which version of UV completable?
I didn't say UV completable. I didn't say it is not. I said it is by itself not UV complete. It is perhaps possible to add other fields which will make it UV complete. In this case, I know that if we add enough gauge fields, it will be UV complete. But I assume, of course, I need to prove that, but I assume, and that's a safe assumption, that adding a lot of gauge fields will completely change behavior and the symmetry breaking pattern will disappear.
Yeah,
That's the assumption. I assume that this interest in exotic behavior will be completely washed away if I start adding additional fields to make it UV complete and weakly coupled in the UV as we usually have with the gauge fields. Okay, so recently interest in this topic was reignited, and the Israeli group and together with Zahar Komargotsky, they wrote several papers essentially revisiting this bivector model. And they wanted to see if they can actually engineer a model which is UV complete first, and second, symmetry breaking persists to infinitely high temperatures. That was the motivation, because at least Zahar was very much motivated by the black hole connection. But of course, it's a question in its own right. You just want to see if in field theory you can have such a phenomenon. So they consider this bivector model, and it worked quite nicely. Everything is fine, and you have all the properties you want, except that you are forced to work on 3 minus epsilon dimensions. They were using the Wilson expansion. And you cannot take epsilon to be 0. If you take epsilon to be 0, then all of this interesting behavior disappears. You are forced to work in the fractional number of dimensions, which is not quite okay because it doesn't quite describe the real world. And moreover, this theory is not unitary. So as an effective model, that probably would be okay if you try to describe Euclidean physics. But since this model describes Minkowskian physics, it's not unitary, it's not okay. So we have to say that this is not a genuine example we want. Another follow-up papers also by Israeli group, where they considered a model not in 3 dimensions, but in 4 dimensions. And that was a vector model, and they formally take the number of colors to infinity, which of course very much simplifies the dynamics. And they saw some very interesting behavior, and they saw the conformal manifold and many interesting things and symmetry breaking. But unfortunately, once you have 1/n corrections, nothing of that survives. Okay.
Sorry, that was the same model, but conformal model.
I think it's, excuse me,
So,
this model, yeah,
No. This 1/n corrections restore the symmetry. Which model was it for?
I think it was this model, and I think in this case, they engineered the model to be conformal. I think they engineered the model to be conformal. So those examples did not quite work. And
This is very in the same pattern. If you take 2D, you see deep Hawk model
Mhm.
at n equal with one flavor, let's say, at n equal to infinity, you have a psi bar psi condensate and the massless piles.
Mhm.
But the piles being massless and Goldstone, they are not interacting at this limit. If you include 1/n corrections, they acquire a mass. There is no more spontaneous breaking of the signal.
Very similar, very similar. So it looks like you try and you try hard, but it doesn't work. And when it happens, we usually tend to conclude that this is impossible. But if this is truly impossible, then we should have a theorem that this is impossible. But it's also very difficult to prove a theorem that something is impossible. So that makes it an interesting and open question. And then even more recently, together with Israeli group and together with Misha Goitman, we have been working on a slightly different modification of this model. This is, so let me first outline the question. So the question is, can I have a model of persistent breaking? Is it possible to have such a model that it would be a unitary model, no fractional dimensions, and it will be UV complete? I will not have this situation that I'm secretly describing in lattice. So that's my question. And it looks like, and I want to work in 2+1 dimensions. I also want to go against the Mermin-Wagner. And it looks like that this is possible. It looks like that this is possible, and this is the main result, which I'm going to describe in the next 25 minutes. And this is the work I'm doing with my collaborators together with Misha. And we are basically sticking with the same vector model. We fine-tuned this bi-vector model to be conformal, so on and so forth. What's the secret? What's the new ingredient? I'll tell you right away, the new ingredient, our model is non-local. It's still an interesting model because despite being non-local, it is conformal. We don't prove it is conformal, but we check, and it's not quite a trivial check, and it seems to be, and I will give you additional arguments. So I think this is a conformal model. Since it is conformal, it's okay that it is not local because it's still a field theory.
Is it causal?
I hope so.
Local theories, usually they are non-causal.
That's actually, it's, I think it's unitary. We check that. We cannot prove that, but we check that. With causality, I thought it would come from unitarity, but now since it is non-local, I have doubts.
Okay.
I have doubts. I need to think about it. If it was local, then unitarity and causality would be in the same boat. But now I need to be more careful. I hope, though, that this model can be realized as a lattice model, but this is not set in stone yet.
But you consider honest to God 3 dimensions, right? Not 3 minus epsilon.
Honest to God, 2+1 dimensions.
Okay.
Yes, that's important.
Are you sure it's unitary? Like, is that something you can prove?
And this is something we can check consistency. I'll talk about that, what we did.
And capital N can be arbitrary.
Pretty much. Yes. The point is n is not infinity. If n is infinity, that's cheating, right?
So O3 cross O2 is within this range.
O3 cross O2 is not, but O7 cross O2 is. The difference, it so happens that the difference between those ranks should be at least 5. So happens. Probably not something fundamental. Okay. Right. So this is our result, and I immediately have a question which is not covered by our result. That's an open question, I do not know what kind of type I have here, doesn't matter. But the question I have, okay, once we have this non-local example, the question is, can we actually return back and think about a local example, which will accomplish this either in 3+1 dimensions or in 2+1 dimensions for discrete symmetry. There is no, as I was trying to say, there is no no-go theorem. There are arguments, but there is no no-go theorem. And this is hypothetically possible, also very difficult to achieve. Nobody achieved it before us. We didn't achieve it either because this is for local theories. So that remains as a big open question. And if this is not possible, then it would be great just to prove that this is not possible. Okay, now I will quickly describe the model, but before actually describing our model, I will describe ON model. And this goes under the name long-range Eisen model. You start with the Gaussian, meaning free field theory, which has a quadratic action. It's non-local, so it's already in the coordinate space. You have x1 minus x2 with the polynomial interaction between them. And since it's a Gaussian theory, everything is well defined. You put it in the exponent, so that gives you the Green's function. There's nothing, no complications. And then you can perturb it by a quartic potential. And you can fine tune the dimension of, you play with the dimension delta of this guy phi. And if you take delta to be related to this number of space-time dimensions according to this formula, with positive epsilon being very, very small, then you essentially fine tune phi to the fourth operator to be weakly relevant. And if you do that, then you can study this interacting theory using conformal perturbation theory, basically expanding at leading order in epsilon. And you will see that there is a non-trivial fixed point. It's an interacting fixed point. And in that interacting fixed point, it's very close to the origin. Coupling constant will be of order epsilon. At the interacting fixed point, you can show that it is actually a unitary conformal field theory. Also, it is non-local. So that was done recently by Slava Ryczkov and his collaborators, and that generated a lot of interest. Okay, so this is just one vector model. Our model is basically two copies of this theory, weakly coupled with each other. So this is our model. We have two vector fields. We have two dimensions. A priori, there are two different dimensions, both fine-tuned such that corresponding phi to the fourth guys are weakly relevant. And then you also have a cross term, which is also weakly relevant. And in principle, you have those parameters epsilon 1 and epsilon 2, which control the dimensions delta 1 and delta 2. But since the kinetic term, and that applies to our model and to long-range Eisen model, since the kinetic term is not local, UV singularities cannot renormalize it. And therefore, this delta doesn't flow with the RG flow. That's just a parameter of the model. You set it up in the UV, you go along the RG flow, it remains as it was, right? So this is just parameter which is set fixed. But then you have local operators which are getting renormalized. So you calculate some loops. But in this case, you just do things linearly in the epsilon expansion. That's the conformal perturbation theory. You got your beta function equations. You equate them to 0 and you find fixed points. And there are fixed points. And they are parameterized by the ranks of the global symmetry group. And they're also parameterized by the parameters epsilon 1, epsilon 2. But instead of talking about epsilon 1 and epsilon 2, you can factor out the epsilon scaling because it's small and everything scales linearly in epsilon. So you can just factor it out. It's a parameter, but everything, if you introduce correct notations, everything will be trivially dependent on the joint scale. And then you have one non-trivial parameter, the ratio of epsilon 1 and epsilon 2. Alpha is a dimensionless parameter, which you set in the UV and which parameterizes your theory. Yes.
Could you explain why you don't have interaction terms like phi1 dot phi2 squared?
You can have, you mean phi1 squared?
Phi1 dot phi2 scalar product.
Because it will not be invariant under the symmetries.
Okay.
We want to preserve the symmetry. Okay, this is our model. And I probably already explained this slide. So this is the beta function, general expression for the beta function at the leading order conformal perturbation theory. C are structure coefficients. I can use the language of structure coefficients because Gaussian point is conformal as well. So I can talk about structure coefficients. Then you can take these equations, take these expressions, equate them to 0. And let us first consider infinite n limit. That will be simple. I'll consider infinite n limit. The ratio of ranks, I will consider x. It will be a fixed parameter. So besides x, my theory also will be dependent on this parameter alpha. So I have two parameters, x and alpha. So apparently in the infinite n limit, things degenerate. Exactly how it was for the bivector models considered by Israeli group and Komargotsky a year ago. They considered different models, and Misha commented on a similar phenomenon in 2 dimensions. In infinite n, you have certain interesting degeneracy. Your fixed point equations become this. And these equations, there are 3 couplings, G1, G2, and G3. You introduce some nice notations such that you have tildes now, and these are finite quantities. G1, G2, and G3, you have 3 couplings. And in the space of 3 couplings, this equation tells you that the space of solutions belongs to a plane. And this equation tells you square plus square plus square is equal to a constant, that your solution is a circle. So now we have a fixed and conformal manifolds of fixed points. If I formally take n to infinity, I have a UV theory, which is parameterized by some alpha, but I cannot just take any alpha. In this case, equations degenerate, and I have to force to take alpha equal 1. If alpha is not 1, I don't see weakly coupled fixed points. But if alpha is equal to 1, I not only have fixed points, I have the whole line of fixed points, which nicely become a circle. So this is a space of G1, G2, and G3, and I have a bunch of different circles. Don't look at this plane, please. Just disregard this plane. I have different circles because I can have different parameter x, which corresponds to different ratio of the ranks of my global symmetry group. Okay. So I have different m and n, and for different m and n, I have different circles. All of those circles intersect at 2 points. What is this point? This point is very special, but it is universal to all of those theories. That's the point where OM cross ON minus M symmetry is enhanced to OM. That's completely clear, and that should happen at all n, and this is this point. In the infinite n limit, apparently there is an emergent Z2 symmetry with respect to the sign of this G3 coupling, and therefore there is also the same point where all of those circles overlap, intersect. But this point is very weird, and I don't fully understand it. I think it's not quite physical, because at that point, symmetry is not enhanced to OM, because you have 2 ranks and you have negative G3. Negative, it's not positive. Well, in this point, it's positive, but in this point, it would be negative. It would be this value, but negative. And it means that the symmetry is not enhanced to the full symmetry. So I think this is sort of like a fake point, an artifact of infinite n, which makes G3 independent of its sign. Okay, this is infinite n. That gives you some intuition. What happens if I have finite n? If I have finite n, I already don't have the whole line of fixed points in a given theory. I don't have that anymore. But what I have is the following. Let's turn off interactions, and let's go back to my Gaussian model. As I said, my Gaussian model is parameterized by 2 parameters, epsilon1 and epsilon2. So in fact, I have a somewhat unusual situation. I have a whole 2-dimensional space of Gaussian models. And I can start perturbing my Gaussian, any of those Gaussian models by quartic couplings. So starting from any of those UV points, I can start flowing somewhere. And pretty much that's what happens. I can start with pretty much any UV point, and I can start flowing, and I will flow somewhere in the infrared. So apparently any such model, well, or at least an open set of such models, will have a counterpart in the infrared. So basically it means that if n is very, very large, I cannot have arbitrary alpha, but I can start taking any alpha which is sufficiently close to 1. And then for any value of alpha, I will have a solution which is a fixed point. But apparently it will not be one solution, it will be 2 solutions. And mathematically, if you try to solve it in the large n limit, you will have to intersect one of those circles with this line. excuse me, with this hyperline. It's a hyperline. It's a codimension 1 surface, and then points of interaction will be giving me non-trivial fixed points of this large but finite N theory. Okay, so what is important here is that there are two intersection points, one with positive G3 and one is negative G3. Why this is important? Because different values of sign of G3 will give me completely different phenomenology when it comes to effective field theory. So let me shift gears, and I was considering finite but large n. Let me consider small n. Let me consider n of order 5 or 10. I will have some complicated equations, which I cannot solve analytically, but I can, of course, solve these things numerically. And what I see numerically, that pretty much there is a range of parameters alpha. For some alphas, I don't see any fixed point, but for certain values of alpha, I usually have two fixed points with different values of G3. And in certain cases, G3 becomes negative. At least in this range of alphas, G3 becomes negative. Okay. Oh, good. I need maybe just to speed up just a little bit. Why I care about negative G3 will be clear in a second. Now, I will spend 1 minute explaining what kind of checks we did to check unitarity and analysis, unitarity and conformality. To check unitarity, we calculated, and I should rather say Misha calculated, I have very little contribution in that regard. The anomalous dimensions of operators, and they all happen to be real, which is a necessary condition for unitarity. If they were complex, which is a possibility, then we would know this is not unitarity. They all happen to be real, which is a consistency check. It's not a proof. And with conformality, you can calculate two-point function, and it's a necessary condition that it would vanish unless dimensions of these two operators vanish, and it does vanish in all of those cases. Then you can also calculate three-point function, which has a very peculiar, well, very particular structure. Wouldn't call it peculiar, very particular structure in conformal field theory. And again, it was satisfied at leading order in conformal perturbation theory. So there's a non-trivial checks, and they all work, which gives us some confidence that we are dealing with a conformal field theory, which is good. Okay, now let's discuss low energy physics. Low energy physics works in the following way. You have effective potential, and in this effective potential, you have quartic couplings. And you have three couplings, G1, G2, and G3, and G1 and G2 always have to be positive, otherwise your theory is unstable, but G3 can be negative. If G3 is positive, nothing interesting happens, but if G3 is negative, you can see that something interesting can start happening. If you start heating your theory to find a temperature, then because of this phi squared, which is an analog of sigma squared I introduced in my very first slide, at finite temperature, phi squared will acquire a web, excuse me, it's not web, it's a thermal expectation value, just because you have to sum in the loop over Matsubara frequencies. So now you have non-trivial expectation value, and since you have quartic couplings will generate effective masses. That's all a standard story. Nothing is new or revolutionary here. But if you look at this expression for the mass, I'm only writing a one for simplicity. You can, of course, have expression for it too. If you're writing a mass for one field, then you will see that if both G1 and G3 are positive, mass will be positive and nothing interesting will happen because positive mass will simply make the minimum of the potential at the origin. But if G3 is negative, it is possible that this term will win. If this term wins, M1 will be negative. And if M1 is negative, it means that phi1 cannot be zero. You'll have a negative potential like in the standard model, and it means that it will have spontaneous symmetry breaking right away. Of course, the potential will be stabilized by the quartic term, but phi1 0 is not a minimum of your effective potential. So our job, yes.
But at this moment, if I understand correctly, G1, G2, and G3 are kept your phenological parameters.
Well, they should be taken as critical values in the interacting fixed point. I start with the Gaussian model in the UV. I introduced couplings. I have a flow to some fixed point, which is interacting. I calculated values of G1, G2, G3 at that fixed point. And now I hope that those would be such that M1 will be negative.
Right.
At the point of this slide, there are just phenomenological parameters, but immediately next step, I'm plugging values at the interacting fixed points.
Okay.
Yeah. So that's the logic.
Yeah.
Okay.
It's making the content matter people thought about this for a long time and never could find it.
Okay, maybe they didn't start with a non-local
Sure,
model.
absolutely.
That's likely the case. So of course, this is a very general discussion, but obviously I'm thinking that G1, G2, and G3 are couplings at the interacting fixed point. So the question is, in all of those zoo of theories I discussed, and there are some beta function equations, equate them to zero, solve them, blah, blah, blah. That's all behind the curve. Can I find a point such that G3 is negative enough such that this is negative? The answer is yes. And well, I'm explaining that if mass is negative, you cannot sit at the top of the potential. I hope that's completely clear to everyone here. And let me immediately say that if phi1 acquires a wave, that means that you have spontaneous symmetry breaking. It happens at finite temperature, specifically at finite temperature because mass was generated by temperature effects. And it will persist to all temperatures, and that's important. It will persist to all temperatures, but because my theory is conformal, or at least scale invariant. It was a fixed point I'm working at. I'm sitting at the fixed point. My theory is scale invariant. Temperature is the only relevant scale. As soon as I have symmetry breaking at any temperature, it will persist to all temperatures. And the theory is UV complete because it's a CFT. Okay. So now I'm showing exactly the same plot as before. These are my possible alphas. These are the values of my parameter alpha. This is for the theory with n equal 1 and n equal 6. And there are a lot of, there are a lot of different alphas where G3 is negative, but negative G3 doesn't necessarily mean that the mass is negative. But there is a very small region, which is highlighted in orange, where G3 is negative and mass is negative. If you start increasing n, then you will have bigger and bigger ranges. This is sort of the first smallest n for which this is possible, m equal 1, n equal 6, and then the region is small. But it doesn't matter. That's a proof of principle, and you can see numerically that whatever larger m you stick in, it always works. And mathematically, that's not an analytic result. That's a result of playing with Mathematica and solving equations numerically. Apparently, if n is larger than m plus 5, then you always have this region where you have spontaneous symmetry breaking at finite temperature, and of course it persists to all temperatures. That's pretty much all I wanted to say about this model. I'm done with this model. I maybe went a little bit fast through technical details, but I think the idea is clear. I have 3 minutes maybe to conclude, 2 minutes to conclude. So we have a model that goes against Mermin-Wagner. It avoids Mermin-Wagner by virtue of being non-local. We understand quite well what is the technical argument. The sigma squared or phi squared is finite, and that's exactly gives me the mass, and that's what works. But there are things which I don't quite understand, including the entropic argument. And I want to understand it because, well, the natural question, what's beyond, what are the lessons to learn? One lesson to learn is that I really want to have a local model which would break discrete symmetry in 2+1 dimensions. There is no-go theorem against that, and this is still seems impossible. Then I want to have a theorem. And then the question is, what can be done in 3+1 dimensions? And if lessons learned for this non-local model can be brought to holography. That's non-trivial because non-local model has no stress energy tensor. So it means that there is no dual gravity. It's something. Maybe it's a vector model, maybe something like Vasilyev's theory, where really black holes is not something, well, Vasilyev's theory is not a local theory in some conventional sense. So there is no immediate lesson for holography from my example, but if I only manage to have some local examples, then there immediately would be some lessons for holography. So that's one very interesting direction. And second one, I want to think about lattice models. And for that, of course, I need to understand the entropic argument. And second thing, it's clear that I want to consider lattice models with a long range interaction. And then, at least at my level of knowledge, it's not even clear if such a lattice model necessarily would have symmetry breaking, excuse me, will have symmetry restoration at infinite temperature. It's just maybe this question is answered in the literature, and then I'm wasting my time. But the question is pretty much like that: can I have non-analyticity at the point beta equals 0? As a mathematical physics question, it's a very well-defined question. It's either has been answered in the literature and I simply didn't find the answer yet, or then the question, if it hasn't been answered, then the question is to go and to investigate it mathematically. It's an excellent question. I know how to solve this problem for short range. Of course, it was done before me, but then I cannot immediately extend the short range techniques to long range techniques. And the problem is exactly the same. You try to calculate free energy and it has infrared divergences, and you need to avoid having those infrared divergences because they can give you a singularity already at beta equals 0. So there are questions. We have an interesting example, which maybe emphasizes some directions, but doesn't really provide final answers. So I think we are in a good position to continue this. Thank you.
Time for question? Yeah, may I ask a question? Could you go back to your condition for m larger than? So
Yes.
I can pick 2m, right? I can take m equals 2, and then what your theory
No.
valid for O2 cross O2?
Well, you can take n equal to m, yes. You can, excuse me.
Yeah, so
Well, if you want to have spontaneous symmetry breaking, then n has to be larger than the largest of those two numbers.
larger or equal?
It has to be equal to the larger
Oh,
of
okay.
those two numbers.
Okay.
If m is small enough, 2m will not, the gap, well, the difference between ranks should be 5. I do not know where it's coming from. I found that using Mathematica and numerics, right? So, I don't know what is fundamental. Yes.
I would naively expect that the orange region extends up to the most negative point in the vertical direction. Why it stops so early? Because
In this, maybe it extends to the point where like smallest alpha.
yeah, it should extend to the.
It might be, maybe it extends to the point of smallest alpha, and with the quality of this plot, that very well could be.
So you never zoom into that.
No. I don't see an importance of this extending exactly to the smallest value of alpha.
I'm not talking about alpha. I'm thinking it extends to its massive value of G3.
G3 is on this.
Yeah,
I don't think it extends. The smallest value of G3 is here. I don't think it extends to this point.
Yeah, that's counterintuitive because G3.
I agree. But this plot shows you G3, but of course, this plot should be shown as a one-dimensional line in a three-dimensional space of G1, G2, and G3. So this line has a value of G1 and G2, and it's likely that G3 is smaller here, but G1 is larger. And that's why it doesn't work, right? So it's a multi-dimensional surface. Yeah, I do not know if there is much importance in studying this geometry in detail. The point, of course, is that such a point exists, or such a range exists. And then how exactly it looks, it might be interesting, but I'm not sure what is the lesson we learn if we understand it in detail. Yes.
Very brief, short remark or question. There are infinitely many non-local field theories.
Yes.
And as far as I know, most of them are acausal, which is obvious that they are because you have instantaneous interaction at two distinct points, right? And they are not related by a wave propagating with the speed of light and so on.
Yes.
So I'm not so sure that the model you presented is good from this standpoint. Or maybe it's on the contrary, you can say, aha, this is a model which we want to have for some reasons. Okay, it's a causal, the better for us. This is a model of maybe some events in our world are not causal, but acausal, who knows?
I would say it is a very good question, which I haven't think about whether this is a causal theory, and that would be something to understand. And the second part of it, maybe I should forget about time, reduce this theory to be two-dimensional effective field theory with this kind of long-range potential.
Okay.
And I will say it's a description of some long-range interaction, like the Eisen, long-range Eisen, that you can realize with the spins on a lattice. So that's completely physical, right? So the hope would be that I can discretize that and think about this as some coarse-grained description of some physical system. And
Of course, if it's statistical physics,
then I will
then
become
all time
Right.
you're just dealing with the equilibrium or
Exactly,
non-equilibrium.
exactly. Then I should reduce it to two-dimensional, to be genuine two-dimensional. That hasn't been done, but that potentially can be. I cannot guarantee that everything will work, but at least it's very clear what has to be checked in this case. I have a question. Yes,
So
please.
we really should leave within the next, certainly within the next 2 minutes. to be good.
Okay.
Quick question, so 1 plus 1 dimensional system, is that possible to have a symmetry?
In one dimensions?
Yeah, 1 plus 1.
I don't think so. No, I don't think so. I think there are theorems that fluctuations are so large in one dimensions. Statistical mechanically, that's very clear. You have theorems from 60s that things are analytic in the full complex plane of beta, right? That's very clear. And physically, the fluctuations in one dimensions are infinitely large, so you can never have an ordered phase. Then there are, of course, different exceptions with the non-traditional phase transitions where the order parameter is not a local order parameter, but that's not what we're discussing here.
So even for discrete, even for discrete symmetry.
Even for discrete symmetry, if it's a local order parameter, that's not possible. You can have phase transitions where the order parameter is something like entanglement entropy, right? Whether this constitutes a genuine phase transition goes well beyond this seminar, but those kind of things are possible.
Very quick question for 10 seconds. Is the transition first order or continuous? The one that we described, when G3 is negative, such that mass becomes negative.
I think it's a second order phase transition.
But isn't then the phi field immediately acquires non-zero expectation value, finite expectation value?
No. Sorry, it will be like a bubble, right? Well, it's a question.
First order.
It's a first order. It's
First order.
It's a first order. It's
Right. Then obvious question, if it's first order,
Yeah.
are you guaranteed that you don't need higher order terms in expansion and phi?
well, that's easy. That's easy to understand. If you have an effective potential, there will be higher orders in phi, and they can change the value of the minimum, but they can never push it back to the origin because at the origin, mass dominates.
How do you know it's first order?
But listen, no, let's forget about the order. Let's forget about the order. If you have an effective potential and you can have minus negative mass squared phi squared, then whatever you write at high orders in phi, it will be not important in the vicinity of origin.
Right, but you don't know the state, right, at the same time.
Well, the state will be space invariant. It will be phi with non-zero. We should go, right?
Okay.
So we can continue.